Hello students, welcome to EPG Pathshala. I am Dr. Varun Vyas from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Bridges Controlled Circuits Part 1 from paper Measurements and Instrumentation. In this module, we will study about various kinds of bridge circuits. First, we will study about the bridge control circuits and various type of bridges that are used for measuring unknown resistance. Under DC bridges, we will study about the Wheatstone bridge, its circuit design and its sensitivity. Then we will study about the Kelvin double bridge and how it is used for measuring resistances less than 1 ohm. This module is aimed to study various methods involved in measurement of unknown resistance. The choice of suitable method for measurement of resistance depends on the number of factors. One such factor would be the range of resistance to be measured, that is, low, medium, and high. Other factors may be required for the accuracy of measurement and working conditions, etc. Low resistances, a resistance of 1 ohm and under are included in this category. Measurement of low resistances is required for determination of resistance of armatures and series field windings of large machines, ammeter shunts, cable lengths and contacts, etc. Next is medium resistances. The resistances ranging from 1 ohm to 100 kilo ohms fall into this category. High resistances. High resistances above 100 kilo ohms are included in this class. The measurement of high resistance is required for determination of A. Resistance of high resistance circuit elements, B. Insulation resistance of components and built up electrical equipments of all types, C. Volume resistivity of the material, D. Surface resistivity. For measurement of resistances belonging to the above discussed categories, various types of bridge controlled circuits are used. A bridge control circuit is an electrical circuit where two parallel branches are interlinked via a third branch at an intermediate point between the parallel branches. Initially, bridge circuits were designed for laboratory purpose, but now similar circuits are used for linear and nonlinear measurements, power conversions, instrumentation, and filtering. In simpler terms, besides measuring impedances, bridge circuits are also used for altering signals from transducers with associated current and voltage signals. Now, there are two types of bridge circuits. DC bridges, they use DC voltage and are used for measuring resistances, whereas the AC bridges are used over alternating voltage and measuring impedances of circuits consisting of capacitor and an inductor. There are two types of AC bridges. First is Wheatstone bridge and the second is Kelvin bridge. And we have various types of AC bridges. First is a capacitance comparison bridge. Second is Wien bridge. Third is inductance comparison bridge. And fourth is a resonance bridge. DC bridges. Now we will look into Wheatstone bridge. The earliest example of bridge circuit is Wheatstone bridge. In 1833, it was Samuel Hunter Christie who came up with the concept of bridge circuit, which was known as diamond method due to diamond-like shape of the electrical circuit. It was 10 years later, in 1843, Charles Wheatstone introduced few modifications and promoted it as a better method to measure resistance of an unknown resistor. Besides digital multimeters, a Wheatstone bridge can be used for measuring resistance down to milliohms range. The circuit diagram for the Wheatstone bridge can be seen in Figure 1. A Wheatstone bridge consists of 4 resistors, where R1 and R3 are of known values, R2 is a variable resistor, and Rx is the resistor whose resistance is to be determined. The branch that interlinks the two branches has a galvanometer Vg to measure the current flow between the two branches. If the current between the two branches is not zero, variable resistor is adjusted to bring current flow to zero between point D and B. Now, according to the Kirchhoff's second law, the net voltage of the loops A, B, D, A and B, C, D, B should be equal to 0. The equation for the both loops can be written as: for loop A, B, D, A, I3 dot R3 minus IG dot RG minus I1 dot R1 is equal to 0. This is equation 1. For loop B, C, D, B, Ix dot Rx minus I2 dot R2 plus Ig dot Rg is equal to 0. This is equation 2. When net flow between the point D and B is 0, that is when bridge is balanced where Ig is equal to 0, then I3 dot R3 is equal to I1 dot R1. This is equation 3. And Ix dot Rx equal to I2 dot R2. This is equation 4. Now, according to the Kirchhoff's law, the net current at point B is given by I3 minus Ix plus Ig equal to 0. This is equation 5. And at point D is given by I1 minus I2 minus Ig is equal to 0. This is given as equation 6. Therefore, when bridge is balanced and equation 3 and 4 are divided and we rearrange them, we get Rx is equal to R3 dot R2 divided by R1. This is equation 7. Briefly, the value of unknown resistor Rx can be determined when value of other three resistances, that is R1, R2 and R3 are known to us. It should be noted that the relationship between the resistances will still hold true even if battery and galvanometer are interchanged. Now we will look into the advantages of the Wheatstone bridge. Advantages: since the net current across point B and D is null, that is 0, this type of DC bridge is also known as null type DC bridge. Here, inaccuracies that may arise due to instrument calibration can be easily avoided, as galvanometer is simply used for measuring zero current. Another advantage of this method is that any errors due to fluctuations in EMF source can be avoided, as the balance of the current is quite independent of the EMF source. And at reduced sensitivity, this system has a range of 1 to 10,000 ohms and can be further extended. The precautions that we should take and precautions that should be taken when working with a Wheatstone bridge. While measuring an unknown resistor, one should take the following precautions. Galvanometer should be well shunted in order to avoid deflection during early stages of the operation, and one should reduce the shunt resistance as bridge approaches the balance position. This also increases the sensitivity of the galvanometer. One should always switch off the battery before the galvanometer key and open after it. This will reduce any EMFs due to rapidly changing current in case resistor under test is inductive. This too will prevent any violent deflections in galvanometer. Measurement should also be conducted by reversing the battery, and means of 2 should be taken as correct value. This will avoid any errors due to thermoelectric EMFs. Now we look into the sensitivity of the system. The sensitivity of the Wheatstone bridge. In a slightly unbalanced bridge, sometimes it is desirable to know galvanometer response. This helps in selecting a galvanometer sensitive to unbalance in a specific bridge arrangement. It is used to determine minimum unbalance that can be observed with a given galvanometer for a specified bridge, plus it helps in determining minimum deflection to be expected for a given unbalance. By solving bridge circuit for the small unbalance, one can calculate bridge sensitivity SB. Let us assume bridge in figure 2 is perfectly balanced such that P by Q is equal to R by S. This is equation 8. And to create a small unbalance, the resistance of the R is changed to R plus delta R. Then open circuit voltage E for the given bridge can be written as E is equal to EADC minus EABC. This is equal to I2 into R plus delta R minus I1 dot P. This can be written as E divided by R plus delta R plus S. This is multiplied by R plus delta R minus E divided by P by Q multiplied by P. Then small e is equals to E multiplied by R plus delta R divided by R plus delta R plus X minus P divided by P plus Q. This is equation 9. This equation can be further rewritten as E equals to E multiplied by R plus delta R divided by R plus delta R plus S minus R divided by R plus S. Since P by Q is equals to R by S, or that can be written as P divided by P plus Q equals to R divided by R plus S. By further solving and rearranging the above equation, we get E is equivalent to E into S into delta R divided by R plus S whole squared. This is equation 10. For a balanced bridge, while solving for the above equation, the second and third order terms in power expansion may be neglected. Now for voltage sensitivity SV of a galvanometer is defined as the change in scale units per unit change in voltage in the galvanometer circuit when the total resistance seen from the galvanometer circuit is that of a specified dampening. Galvanometer deflection theta is equals to SV into E, which is equals to SV E into S into delta R divided by R plus S whole squared. Therefore, the bridge sensitivity SB can be defined as the deflection of the galvanometer per unit fractional change in the unknown resistance, which can be written as SB is equals to theta divided by delta R, which is divided by delta R. This is equals to E into S into R into SV. This is divided by R plus S whole squared. This is equation 11. Now we look into a variant of Wheatstone bridge, that is Kelvin bridge. Minimum resistance that can be measured accurately with Wheatstone bridge is 1 ohm. To measure a resistor having a value below 1 ohm, a Kelvin bridge is used. A Kelvin bridge is also known as Kelvin double bridge and Thomson bridge in some countries. A Kelvin bridge has two extra resistors that form a set of ratio arms, hence named double bridge. This modification eliminates the effect of contact and lead resistance while measuring a low resistance. Here, resistors within the range of 1 ohm to approximately 1 microohm can be measured with high accuracy. This modified form of Wheatstone bridge is shown in the figure 3. Here, X is the resistor of unknown resistance and resistance S is the standard resistor of the same order of resistance and the same or the higher current rating as compared to the resistor under test. P, Q and small p and q are non-inductive resistors with two ratio arms similar to Wheatstone bridge interlinked via galvanometer G between point F and K. A rheostat along with an ammeter is there for convenience only. During the measurement, ratios P by Q and small p by Q are varied until galvanometer reads 0. When both the ratio arms are balanced, we get the following equations according to the Kirchhoff's second law for the two meshes A, H, F, K, B, A and F, E, D, C, K, F. The equation 12 is I dot P minus I dot small p minus I dot x is equals to 0. This can be written x as I dot x is equals to I dot p minus I2 dot small p and I dot q minus I2 into small q minus I dot s is equals to 0. This is equation 14. This can be written as Is is equals to I1 dot q minus I2 dot small q. This is equation 15. By dividing equation 13 and 15, we get x divided by s is equals to I1 dot p minus I2 dot small p, which is divided by I1 dot q minus I2 dot small q. This is equals to p, which is multiplied in brackets with I1 minus small p by p into I2, and this upper term is divided by Q into brackets I1 minus small q by Q into I2. This is then equals to P by Q. Since small p by P is equals to small q by Q, hence the value of the unknown resistance X is equals to I dot into brackets P by Q. This is equation 16. Operation of Kelvin double bridge. The method of operation of Kelvin bridge is slightly different from what is described earlier for Wheatstone bridge. During the measurements, P, Q and small p and q are known, and fixed standard resistances and their temperature coefficients are also known. The resistance of such values that P by Q is equals to small p by Q. Then P is equal to small p and Q is taken equal to small q, and the ratio P by Q is equal to small p by Q is made approximately equal to X by S. In case approximate value of X is unknown, then it can be either determined with voltmeter ammeter method or by potentiometer method. Thereafter, the unknown resistance X is shunted by a variable resistance whose value is known, and to obtain the balance, the value of the shunting resistance is adjusted. With shunting of unknown resistance X by a variable resistance of value R, a balance is obtained, and equation 16 can be written as X prime is equals to 1 divided by 1 by X plus 1 by R, which is equals to P by Q into S. This is equation 17. Then X dot R is divided by R plus X is equals to P by Q into S. This is equation 18. In this equation, the values of P, Q, R, S and R are known. Therefore, the value of the unknown resistance can be determined by substituting these values. Here again, the supply current is reversed and the average value of the two observations may be taken as correct value. This helps in eliminating any errors due to thermoelectric EMFs. The bridge sensitivity is determined by noting the smallest variation in the shunting resistance R that can cause an observable deflection in the galvanometer. The ratios P and Q and the small p by Q are made exactly equal by adjusting the lead resistances which are used for the connections. In this module, we studied about various kinds of bridge circuits. First, we looked into bridge control circuits and various types of bridges that are used for measuring unknown resistances. Under the DC bridges, we study about the Wheatstone bridge, its circuit design and its sensitivity. And in the end, we studied about the Kelvin double bridge and how it is used for measuring resistances less than 1 ohm. Thank you.